So welcome all to the lecture Spline Interpolation. In this lecture, we will discuss linear spline, quadratic spline, and cubic spline. Let us see what is interpolation, what is meant by the interpolation. So we are given a set of points, set of n plus 1 points, x0, y0, x1, y1, up to xn, yn, satisfying some relation y equal to f of x. But we don't know the explicit nature of f of x, the exact form of f of x. So we find the f of x by some techniques, say the phi of x, such that the f of x and this phi of x should agree at the tabulated values. So this kind of process is called interpolation. And if phi of x is a polynomial, this is called polynomial interpolation, and the corresponding polynomial is called interpolating polynomial. So there are different techniques for the interpolation. Newton's forward difference, forward formula for interpolation, backward difference formula for interpolation, Lagrange's interpolation, cubic spline interpolation, and like that. Among those techniques, a low-order polynomial approximation in each subinterval provides a better approximation to the tabulated function than fitting a single higher-order polynomial to the entire interval. So, such kind of interpolation, where a low-order polynomial is found in each subinterval, is called piecewise polynomial interpolation. The obtained functions are called the spline functions. You may heard about the spline. The name spline were adopted from the draftsman's device. They use a thin flexible strip called spline to draw the smooth curve. The points at which the two connecting splines meet are called knots. So the low-order polynomial may be of first degree, second degree, or third degree. So we have different kinds of splines, linear splines, quadratic splines, cubic splines, etc. Of these, cubic spline, that is a spline of degree 3, found to be the most popular in engineering applications. So we will focus on the cubic spline, but initially we will discuss linear splines and quadratic spline, so we can easily handle the cubic spline. So see the figure. This is the linear interpolations. Between each subinterval, or in each subinterval, the interval is connected by a linear splines, means a simple lines. But look, the quadratic spline, each interval is connected by a quadratic polynomial, means polynomial of second degree. But look, the cubic spline, each subinterval is connected by a polynomial of degree 3, means cubic splines. Here you can see that these points are nothing but the points of a sinusoidal function. The cubic spline is very near to the sinusoidal function. So we'll go to the linear spline interpolation. What is linear spline interpolation and how they are formulated with example. So we are given set of n plus 1 points x, I, y, I, where I is from 0 to n. And the spacing between each x values is represented by hi, where hi is equal to xi minus xi minus 1. Means hi is the spacing between the points x values xi and xi minus 1. So we have to find the si of x for the interval xi minus 1 to xi. So for each xi minus 1 to xi interval, we have to find the si of x. Clearly, since it is the linear spline interpolation, si of x represents a straight line joining xi minus 1, yi minus 1, and xi, yi. So we write si of x equal to yi minus 1 plus mi into x minus xi minus 1. We have written in this form to ensure that we have the basic condition that for the interpolation, the given data points should agree, the obtained function should agree at all given data points. That means si of xi should be yi, si of xi minus should be yi minus 1, si of x1 should be y1, and like that. Where mi is nothing but our slope, which is defined as yi minus 1, yi minus yi minus 1 divided by xi minus xi minus 1. You can substitute here instead of x, xi, you will get yi. If you substitute xi minus 1, you will get yi minus 1. So we will see one example for the linear interpolation. We are given the set of data points 1 minus 8, 2 minus 1, and 3, 18, satisfying some unknown function y equal to f of x. We don't know the exact relation connecting these x values and y values. So we have to find the linear spline satisfying the given data and also determine the approximate values of y of 2.5 and y prime of 2.0. So remember the linear spline equation. Si of x equal to yi minus 1 mi into x minus xi. So what is mi? The mi is yi minus 1 divided by xi minus 1. So for the first 2 points, this mi is obtained as yi minus 1. That is minus 1 minus 8, that is plus 7, divided by 2 minus 1, that is 7 divided by 1, that is 7. So the m1 is obtained as 7. So this is the equation for the first spline function. This is the second spline function. So we have to find y of 2.5 means y of y value at x equal to 2.5. So x equal to 2.5 lies between B and C points, these B and C points. So this is the y of 2.5. So we substitute in S2 of x, or the 2.5, x equal to 2.5. So it is obtained as 8.5. So it is 8.5. So this is the value, this is 8.5. And the derivative can be found using the two methods. Both are different. If we find, since this point, this 2 point lies at the boundary, so we can use the two spline functions, S1 of x and S2 of x. If we use S2 of x, then the result is 19. If we use S1 of x, the result is 7. So temporarily we take it as 19. So next we will see the quadratic spline. Let Si of x be the quadratic spline function approximating the real function y equal to f of x in the particular subinterval xi minus 1 xi, where again the spacing hi is defined as xi minus 1. Now let the Si of x and Si prime of x be continuous in the interval x0, x in the whole interval, and let Si of xi equal to yi, that is the basic condition for the interpolation. For all interpolation, all kind of interpolation, we already mentioned that the function should agree at all the given points. So that is why the Si of xi should be yi. We know that Si of x is a quadratic function, maximum a quadratic function in the interval, and then it follows that Si prime of x is a linear function. Means Si prime should be a first degree polynomial. The derivative of the second degree polynomial will be a first degree polynomial. So Si prime of x should be a linear function. So we assume, considering all the above conditions, a form for the Si prime of x. So Si prime of x is assumed that 1 by hi xi minus x mi minus 1 plus x minus xi minus 1 into mi, where mi is nothing but Si prime of xi. So why we wrote like this? Because the first and second derivative of the function should be continuous in the interval x0, x. Here, by writing this form, Si prime of x becomes continuous in the interval x0, xn. But we have to find the form of the Si of x, so we integrate once with respect to x. So we obtained Si of x like this: 1 by hi integral xi minus x whole square by 2 mi minus 1 plus integral of this quantity x minus xi minus 1 whole square by 2 into mi plus ci, the integration constant. So to know the exact form of SI of x, we need to find the Ci. What is Ci? So to find the value of Ci, the form of Ci, we put x equal to xi minus 1 in the spline function. That is spline function Si of x equal to this one. So putting x equal to xi minus 1, this term becomes xi minus 1, that is hi. So hi square by 2, and this becomes again 0. This term becomes, the whole term becomes 0. And since putting xi is x equal to xi minus 1, Si of xi minus 1 should be yi minus 1. So using these conditions, so this is equal to yi minus 1. Therefore, Ci becomes this one. Yi minus 1 plus this term. So that is yi minus 1 plus hi by 2 into mi minus 1. So substituting for Ci in this spline function, the Si of x is obtained as 1 by xi minus x whole square by 2 mi minus 1, x minus xi minus 1 whole square by 2 into mi, plus yi minus 1 plus hi by 2 mi minus 1. So this is the exact form of the Si of x. But still we don't know what is the values of mi. What is the values of mi? We know that mi equal to Si prime of x, but we don't know the values of mi. So to find mi, we use the continuity condition at the nodes, means at the boundaries. That is, Si of xi minus 1 equal to Si plus 1 of xi plus, means just before the xi boundary, xi point, just before the xi point, the spline function is Si of x. And just after the xi point, the spline function is Si plus 1 of x. So at the boundary, since it is continuous, both should be equal. So we utilize this continuity condition to find the mi values. So here we substituted xi. So this becomes 0. And this becomes xi minus 1, that is hi. So this is this one. Simplifying, this becomes hi by 2 into mi minus 1 plus mi plus yi minus 1. And similarly, substituting in Si plus 1 of x equal to xi, this becomes xi plus 1 minus x, that is hi plus 1, and this becomes 0. So the result is like this, minus hi plus 1 by 2 mi plus yi plus hi plus 1 by 2 mi. So they are cancelled, so this is equal to yi. So equating these two quantities, Si of xi minus 1 equal to Si plus 1 of xi plus 1, that is yi equal to this one. We obtained mi minus 1 plus mi equal to 2 by hi yi minus yi minus 1. So this is a form of recurrence relation. It's a continuing relation. We can obtain different equations by substituting different values for I, where I may be 1 to 2n. So we get n equations, mi minus 1 plus mi equal to 2 by hi, yi minus 1, where I equal to 1, 2, n. This I cannot be 0 here, because if it is 0, this becomes y minus 1. If I equal to 0, this becomes y minus 1, which is not given or not defined. So this cannot be 0, so it can be start from 0 to n. So we have n equations, but we have n plus 1 unknown mi values. So we require one more equation or one more conditions to determine the mi values uniquely. So we choose one natural condition is 1 double prime of x1 equal to 0. Means at the end of this plane, this is the mechanical spline just straightens out. So this condition is also called the natural spline condition. And the spline obtained in this way is called the natural spline. That is I double prime of x equal to, here differentiating 2 times, we will get this one, I double prime of x equal to this one. So equating to 0, to 0, we obtained this as m0 is equal to m1. So there are now, here there are n equation, there is one more equation, so there are total n plus 1 equations and n plus 1 unknown mi values. So mi values can be solved exactly or solved uniquely. Now we will see the same example, the quadratic spline. So we are given set of data points, the previous data points. Again, we have to determine the y of 2.5 and y prime of 2.0. So we have n equal to 2 means the points are I equal to from 0, 1 to n. Means there are 3 points and the spacing is 1. Spacing between each interval is 1. 2 minus 1 is 1. 3 minus 2 is 1. And by our recurrence relation, this recurrence relation, putting I equal to 1 and 2, we obtain the equations as m0 plus m1 equal to 14 and m1 plus m2 equal to 38. We also have one natural spline condition, natural spline equation, that is m0 is equal to m1. So substituting here m0 is equal to m1 means this becomes 2 times m0. So m0 is equal to m1 is equal to 7. So we get m2 is equal to 31. So now we can write the form of s1 of x or s2 of x. So here we choose the s2 of x. So s2 of x is like this. Just substituted the m values in the si of x function. So to find the value of y of 2.5, we substitute x equal to 2.5 and it's obtained as approximately 5.5. And the first derivative is obtained as 7.0. We can also find this first derivative at 2.0 by finding s1 of x, since the point 2, x equal to 2, is the boundary between s1 of x and s2 of x. Both should be same, since the first derivative is also continuous in the quadratic splines. So now let us see what is cubic spline. So from the linear and quadratic spline explanations, we set conditions for a natural cubic spline as the first condition, psi of x is at most a cubic polynomial in each subinterval xi minus 1 xi, and psi of xi equal to yi, that is the basic interpolation condition, and psi of x, si prime of x, and si double prime of x are continuous in x0 and xn. And finally, the condition for the natural spline for the end spline, that is represented by for the end spline, si prime of x0 equal to, si double prime of x0 equal to si double prime of xn equal to 0. So to derive the governing equations of the cubic spline, we see that the second derivative of the si of x should be linear. That is, we assume the form si double prime of x equal to, like this, 1 by xi minus x in the mi minus 1 plus x minus xi minus 1 in the mi, where hi equal to xi minus xi minus 1, and this mi equal to si double prime of xi. So we have to find the second derivative. Sorry, we have to find the si of x. So to find the si of x, we integrate twice this function. So integrating once, we will obtain this minus square by 2, this plus square by 2, plus 2 constants will be there. One constant corresponds to this one, because basically here the integration is with respect to xi minus x. Here the integration is with respect to x minus xi minus 1. So there are basically two constants. So when we integrate again once more, the second integration, this becomes plus q by 3. So this 3 into order 2 becomes 6. Here is again q by 6. Here the first constant into xi minus x, and second di into x minus xi minus 1. So this is the form of the cubic polynomial or cubic spline, but here we don't know what are the mi values, capital Mi values, and also the integration constant ci and di. So we have to find ci, di, and also the mi values. So initially we will find the ci and di. So to find the ci and di, we set the conditions si of xi minus 1 should be yi minus 1, and si of xi should be yi. So we obtained setting si of xi minus, here putting x equal to xi minus 1, this term becomes 0 and this term becomes 0. And this becomes hi and this becomes hi. So Ci is obtained as 1 by hi yi minus 1 minus hi squared by 6 mi minus 1. And putting x equal to xi in this equation, this becomes 0 and this becomes 0. And this becomes again hi, this becomes hi. So we obtained di as 1 by hi yi minus hi squared by 6 mi. So our spline function becomes like this. So we substituted Ci and di, Ci and di. But still we don't know the mi values. So to find the mi values, we use the continuity condition of the Si prime of x. So we find the Si prime of x from this equation, from the Si of x, like this. First derivative, this becomes first derivative of this one and first derivative of this one. And it's obtained like this. Now, we also find first derivative for the second spline function. That means s prime of I plus 1. So to find s prime of I plus 1, we initially write si plus 1 of x. So here the I values are replaced by I plus 1. So the si plus 1 of x is equal to, all i's are replaced by I plus 1, that is 1 by xi plus 1, xi plus 1 minus x whole cube by 6, mi, x minus xi plus 1, or x minus xi whole cube divided by 6, mi plus 1, yi, hi plus 1, mi, xi plus 1, yi plus 1, hi plus 1, mi plus 1, and xi. So, and as before, we will find the si prime of I plus 1 by taking the derivative of the si plus 1 equation. Now we use the continuity condition. Just after the xi point or xi value, the spline function is si plus 1 and the first derivative is s prime of I plus 1. Just before the xi value, the spline function is si of x and first derivative is si prime of x. So both should be continuous at the boundary or at the node. So setting the condition si prime of xi minus 1. So we substitute in the previous equation for the si prime x equal to xi, we obtained like this. So simplifying, we obtained 1 by xi yi minus yi minus 1 plus hi by 6 into mi minus 1, this one, plus hi by 3 into mi. These two terms are added. Now similarly, substituting for x equal to xi in si plus 1 of si is prime of I plus 1 of x, we obtain like this. So equating both, equating this one and equating this one, we get this equation. So this is the recurrence relation for the cubic spline, where I can be again 1 to n minus 1, because if we set I equal to 0, this becomes again y minus 1. That is not defined, not given. If we set I equal to n, it becomes a yn plus 1. That is not again given. We are given set of values from 0 to n. So this 1 to n minus 1, that is n minus 1 recurrence relations are obtained. Using this condition or using this equation, n minus 1 recurrence equations are obtained. But we have to find n plus 1 m values to know the exact form of si of x. So we have n plus 1 unknown m values and n minus 1 recurrence equations. So to solve exactly, we need two more equations. So that equations is nothing but we already found that is the equation for the natural spline m0 is equal to mn equal to 0. And for the case of equal intervals, means if the points are equally spaced, all h values are equal. So our recurrence relation becomes very simple, like this: mi minus 1 plus 4mi plus 1 equal to 6 by h square yi plus 1 minus 2yi plus yi minus 1. So this recurrence relation can be used in the case of equally spaced x values. But in the case of unevenly spaced x values, we have to use the previous equation. So we will see the previous example, again the previous data for the cubic spline. So again we have to find the y of 2.5 and y prime of 2.0. So by the natural condition, we know that m0 is equal to m2 is equal to 0. And using the recurrence relation we obtained, simply m1 equal to 80. Because the recurrence relations becomes very simple in this case, they are equally spaced and m0 and m1 are zeros. So m0 and m2 are zeros. So it directly becomes m1 equal to 18. So we find s1 of x and s2 of x by substituting I equal to 1 here and I equal to 2 here. By substituting I equal to 1 here, this is 1 by h1 x1 minus x minus x 0 cube y0 h1 and like that. So it is obtained as like this, and s2 of x is obtained as like this. So now again we find the y of 2.5. Just substitute here because 2.5 lies between 2 and 3. So we use the second spline function s2 of x. So substituting x equal to 2.5, we get y of 2.5 equal to 7.375. And y prime of 2.0 is equal to 13. To find this one, the first derivative at this boundary, we can use both equations, any of the equations. Both will give the same result. So anyway, we found that the cubic spline, surely it is more better than the previous two linear spline and quadratic spline because it is one more higher degree polynomial we are obtaining. So we will do one more assignment. So determine the value of y of pi by 6 using the cubic spline approximation given 0, 0, pi by 4, 1 by root 2, pi by 2, 1, 3 pi by 4, 1 by root 2, and pi 0. Okay, thank you.